Good afternoon, everyone. I'm going to go ahead and get this party started. I'm Tracy Bramble with the Outreach and Development Bureau, and welcome to this edition of the Innovation Power Hour. Innovation means different things to different people, but here at the Iowa DOT, we're simply defining it as implementing a change to improve processes, tools, and relationships to create positive experiences for our customers. One of the ways we're supporting an innovative culture, is to highlight projects and stories of innovations happening around the department. When you read any of the Transportation Matters blog posts that are delivered to your email inboxes or on our website, you'll notice that some of the stories are marked with Iowa DOT Innovates. We've implemented that graphic to start highlighting those stories and talk about innovations across the department. Today, we're excited to continue another innovative outreach, the Innovation Power Hour. Today's Power Hour features Derek Belser, District 6 construction engineer. Derek, along with our construction partners, will take us through the innovations used to replace an existing bridge on Iowa 1 in Van Buren County. By building a bridge under a bridge, the team was able to keep traffic moving during this project. Before we get started, let's make sure that you mute your line, and we'd love you to ask questions, so feel free to post them throughout the presentation in the chat box. I'll read those at the end of Derek's presentation. Excuse me, this presentation is being recorded, and we will be sending out instructions on how to access the recording after today's session. The presentation also counts towards your training and development plan hours, so please keep track of those if you are needing more plan hours. With that, I'll turn things over to Derek and our partners to tell us more about this project.
Hello, I am Derek Belser, and I'm here to talk to you today about building a bridge under a bridge, an innovative way of keeping our customers moving. Innovation in construction. While maintaining safety, innovation can increase mobility in order to keep our customers moving. I'm going to talk to you about a bridge replacement project using an arch on Iowa 1 over Little Lick Creek in Van Buren County. Van Buren County is located in southeast Iowa, just south of the Fairfield District Office. Today's agenda will include concept, design, fabrication, construction, leaving time for questions. Iowa 1 is classified as an area development route with a C maintenance service level, 24-foot wide PCC pavement with granular shoulders. An HMA resurfacing project with paved shoulders was completed in 2004. The 2022 AADT was 2,500 vehicles per day with 9% truck. The crash report from January 1st, 2014 to December 31st of 2023 indicated there have been 3 crashes, 0 fatalities, 0 personal injury crashes, 1 animal hit, 1 operating vehicle in a reckless manner, and 1 vehicle ran off the road to the right. The existing bridge is a 240-foot by 30-foot welded plate steel girder fracture critical structure built in 1967. A bridge deck overlay project occurred in 1992. Conditions of the existing bridge. The deck contains numerous cracks, hollows, and spalls with exposed rebar. The abutments have rusting cracks, large hollows, and deep spalls with exposed steel. Leaking deck joints are accelerating the deterioration of the structure. Due to the condition and being a fracture critical, a replacement was recommended. Replacements considered. Replace the existing structure with a 3-span, 294-foot by 40-foot pre-tension, pre-stressed concrete beam bridge at a 0-degree skew using a detour, or to replace the existing structure with a precast 3-sided structure similar to a Contact B-Boat C series structure. If option 1 was selected, project estimated total was $3.2 million plus the anticipated detour costs. Iowa 1 would be closed and an off-site detour would be utilized. It was anticipated detour would be in place for approximately 165 days. The outer distance travel is 12 miles. The total distance user cost was anticipated to be $730,000, which equates to over $4,000 per day. With an AADT of 2,500, this equates to $1.77 per user per day, plus the additional time associated with driving the 12 miles. If option 2 was selected, the project estimated total was $3.8 million. Traffic on Iowa 1 would be maintained at all times. New precast three-sided structure could be built under the existing bridge without disturbing the bridge. After the precast structure has been placed, flooded granular backfill and flowable mortar would be used to fill the voids between the precast structure and the existing bridge. Alternative 2 was the preferred alternative. Due to lower project cost when factoring in the anticipated detour, safety considerations, and less maintenance associated with the three-sided structure. Based on the hydraulic analysis, a culvert was not an option for this location, so no culvert options were reviewed. Other alternatives discussed included a roundabout option, stage construction, and accelerated bridge construction. A roundabout was dismissed due to the topography. The ABC option would be more expensive and complicated, and the stage construction was also ruled out. Once the Bebo C series was selected, the appropriate size needed to be determined. With a drainage area of 21.9 square miles, the hydraulics determined that the arch needed to have a rise of 26 feet 4 inches, a span of 54 feet, 18 inches of cover at the center of the structure, and be 144 feet long. Based on the size requirements, a twin leaf sectional C54T/6 was needed. Each leaf section is over 28 feet in length, almost 6 feet wide, and weighs 20.8 tons. They were delivered one at a time, connected together with a piece of all-thread rod during installation, later bonded permanently with a concrete pour. The MSC walls needed to be designed along with the barrel section of the arch. The MSC walls were also produced by Contact. Terracon performed the site investigation. Based on the review, they recommended the arch culvert be supported on a spread footing foundation bearing on the underlying limestone bedrock, which is shown here. Terracon's geo report of the rock core from the depth of 21 feet to 26 feet had a 97% recovery, but the RQD was 33%. From 26 feet to 31 feet, the recovery was 100% and the RQD was 42%. Once completed, the barrier rails will be removed, floor slopes will be in place, granular backfill will be held back with the MSC walls, and the traveling public will drive over the arch without their awareness. From this point on, I'm going to enlist the help of some additional people. The first of which is Matt Rasmussen. Matt is a senior bridge engineer with Shimmer & Associates. He obtained his bachelor's in civil engineering and master's in structural mechanics and materials from the University of Iowa. He has 16 years of bridge design and rating experience, from design and ratings of small reinforced concrete box culverts to large variable depth steel girder and pre-stressed concrete structures at river crossings and urban interchanges. During our conversation, Matt was asked to discuss challenges encountered, design focus,
So
and
the
why a
biggest
box culvert
thing
would not have worked.
was the proximity to bedrock and then the unknown aspect of exactly where it was, because the original um, structure, the drawings indicated the bedrock was at a different elevation than the borings indicated. And so not only did we need to design the footings for a long stretch of bedrock, but also you had to build in some conservatism in there so that it could be adjusted in the field by 6 inches or so and not have an issue. And then also provisions for having the contractor verify the rock before that they built. And of course, as you know, in this case, it turns out that the rock was variable beyond even what the borings showed that they did for confirmation. So that was probably the biggest challenge.
So your main focus was on the stems from the bedrock up?
Yep, from the bedrock up, and then making sure there were provisions in place for potential construction issues so those could be solved. And then also the MSE walls, since that is not a typical thing to have in a floodway. The big issue we had there was working with this district personnel, with you guys, and then also the Construction Materials Bureau to see what sort of details they wanted to make sure that it was going to last a lot longer, despite the fact that it was going to be a flooded MSE wall. And so there was a lot more effort than you would normally think was put into detailing and materials and specs to make sure everything that Iowa has in their normal specs would work for this situation as well. Right. And these arch segments are able to pass a lot more water than your typical box culvert is. So it's a solution to a situation where you can't just put a regular box culvert underneath there, but you want something that takes a lot less maintenance and doesn't impact the traffic. So it's a great solution to the problem for scenarios like this where there's a huge water area that needs to pass underneath.
Absolutely. Next up is Jake Vogel. Jake is a senior bridge consultant for Contact Engineered Solutions out of Shakopee, Minnesota. He's worked on numerous projects in Colorado, Minnesota, Iowa, and many other states across the U.S. He received his Bachelor of Science in Engineering in 1999 from the South Dakota School of Mines and Technology in Rapid City, South Dakota. Jake is active in Minnesota Society of Engineers and Surveyors, as well as Minnesota and Iowa County Engineers organizations. And then we have Travis Augustine with Progressive Structures, the prime on the project. Progressive Structures was established in August of 2010 by Travis Augustine and John Moyna. The company was started to better satisfy the demand for underground and structural projects. Moyna has been in the construction industry for 30 plus years with experience in a vast array of underground projects. Travis began operating the company after graduating from the University of Northern Iowa with a degree in construction management.
How do we talk about a project that's as complex as this? Where do we start, right? I think that's on everybody's mind. So at Contech, we do, a fair amount of consultation with consultants that we work with that are in the transportation and heavy highway markets. And a lot of times when they get a project like this, that is a pretty unique challenge. I mean, this site in particular, as anybody who's going to be watching this is probably going to be seeing the photos and the videos. It's a deep ravine. The bridge is a long ways up from where the flow line of the creek is, and these are the types of projects where we get calls from consultants, and in this type of situation, they were originally thinking, well, maybe a bridge, but then they start looking at what the detour plan would have to look like, and that's a pretty big undertaking. So knowing that in mind, I think in this case, Shive Hattery, who did the prelim design, came to us and said, hey, we're actually considering doing some kind of buried structure and having the buried structure stay under the structure and building it underneath the existing bridge so we can keep the bridge in service while we construct a new structure below it. And knowing how much vertical height we were dealing with, I think this was a challenge that Shive Hattery realized that, hey, we probably ought to, check around a little bit and see who does structures that are not only large enough to handle the flow capacity, but also deal with the high amount of overburden. There's just not a whole lot of technologies out there. And as a manufacturer, we do have a few different types of technologies. So at the very onset, we did talk to Shive Hattery about some metal options. And given the amount of flow, it kind of got outside of the realm of what a lot of metal options could handle, and maybe a little more challenging from a cover standpoint too. But we do make a precast arch system called a Bebo system, which looks more like a conventional arch system. Sometimes the DOT folks, especially Iowa DOT, are familiar with our three-sided concrete arches, or what we would call our conspans, which are more of a squatty kind of more of a flat arch top with vertical sidewalls, which we've certainly supplied on state jobs. But when you have a high amount of overburden, a lot of times you need to pick a structure that acts more like a true arch, that actually can shed load out to the backfill when it's feeling all that load from the overburden. So that's really how the discussion started with Shive Hattery. We sort of went back and forth on the options, how much fill could be accommodated, different scenarios, and keeping in mind the whole time too that Shive Hattery did have the ability to possibly make the arch rise up in overall height by making a stem wall taller. So those were some of the considerations. All the while, we're providing some preliminary loads and reactions for them to see what that might look like, so they could hand it off to final design. So we did a lot of upfront assistance with them, if you will, and they laid a lot of different things out from the hydraulic standpoint to lay out what structures might work. So the structure selection was pretty robust, going back and forth, looking at different sizes, span and rise combinations, how they might utilize the stem walls, different things like that. So we did start to get to a point where we had dialed in the arch size that seemed to make the most amount of sense. And of course, that was the final arch size, which ended up being the 54-foot clear span structure, and then about a 26-foot rise, a little bit over 26. So you think about those dimensions, it's almost a true arch, right? The span is basically twice the amount of rise. So it's a very efficient shape structurally. So that's, I think, how we kind of honed in on that. And along the way too, we might have provided them some user-defined coordinates to help them model it, because not everything you find in the hydraulic programs is always everything that's what's available. And sometimes many of the things they show in the HEC-RASs of the world don't always reflect what actually can be built either. So there was quite a bit of back and forth there. So I guess kind of fast forwarding to bullet point number 2. Jobs is because those little things can be a make or break. You know what I mean? If you're out of tolerance and you've got a structure that big, I'm sure Travis asked Solomon probably a million little questions of, hey, how do we adjust this? And he's showing him the tweaks and everything to make sure because if you get off on that footing, there's not a lot of things you can do to rectify things on that long of a barrel. I mean, what were we? Gosh, I want to say we were 144 feet.
Yeah, 140.
You can, if you mess up even a little bit, you can be so off in your alignment in one piece, in two piece, and on a 54-foot span arch, that's not easy to bring it back into tolerance. So every piece that you put in, you've really got to be cognizant of those tolerances. That's why it's so important to make sure, if you're going to vary close to that, take it up to the tolerance, you got to absolutely make sure you've got your plan ready for the next piece. To your point, one of the things that it's hard for people to visualize is when you had your false work in there, it is basically like a splint that's kind of holding them into place. When you pick them with individual cranes, the center of gravity on those precast pieces is wonky. You have these two objects that are just kind of floating around, in space, and they're not just sitting perfectly, where you need to set them down in the keyway and everything. So when you say it was easier to do it with your false work, I would believe it, because you're controlling the amount of movement that arch can have, and then you're actually using the jacks. You're actually able to manipulate the movement the way you want it to. But that's a little more difficult to do with the cranes, because they're just kind of free flowing in the air, and there's a lot of tweaking that has to happen to get them right.
Yeah.
We had to get kind of creative with Travis too on the arches. One of the things that we've glossed over a little bit here is that when I think we were originally talking to Shemmer and Shive Hattery, there wasn't a whole lot of discussion about the arch being a two-piece at this span. At a 54-foot span, our arch comes in two pieces, as was witnessed there in the photos and everything. So not knowing that, a designer might look at that and think, oh, the whole thing's getting just pulled in as one time, or getting pushed in underneath the bridge. And we certainly have precast arches that do that, but unfortunately they end at about 45 foot in clear span. So the structure we had here was actually what we call a twin leaf B-bow, and it had a crown joint in the top of it, and you can definitely see those photos. So what makes that unique is Travis had to come up with a rigging system to be able to hold those two halves together. We do have an alignment rod. It's basically a piece of all thread that is merely something to just kind of hold them in the place during the closure pour on the top. But that all thread rod is not something that has enough strength to hold these two arches together independently while they're pushed. So basically, at a very high level, what Travis had to do, and we had to incorporate this in our shop drawings, is we had to find a way to almost immobilize the halves and hold them together in something that would not allow those two halves to move independently. And when we show his photos of kind of his splint or his rigging to do this, it was a little bit of give and take, and we actually had to add some extra steel into our normal arches above and beyond what they would normally use, to make sure that there would be some extra beef in the areas where he would be grabbing our arches, or basically at our pick points. Keeping in mind that the ideal situation for him to grab our arches would be in areas where they were intended to have lift points when they're lifted off the trucks. So that's how he, in a roundabout sort of way, figured out how he was going to grab them and immobilize them, is he worked around where our typical pick points would be at, and came up with kind of a rough rigging plan for how to do that. So I don't know if at this point in time, Travis, we want to kind of start talking about a little bit about the rigging and how that tied in a little bit, because it certainly was a work in progress. We almost had to break it down and pull it apart to figure out how to put it all together.
Because
Yes.
that is a good segue into, Travis, how did you come up with that framework? I mean,
So it's kind
you
of,
knew how big the arch was going to be
you know,
from the submittal and the shop drawings, but from the plan, how did you develop the size, and where did the railroad tracks come from?
well, so they all kind of came over, multiple conference calls and discussions and meetings. I mean, it really started to come into place. So this thing bid like November, the season before, I think is what it was. And Jake kind of humored me earlier about an hour ago. We were talking about how he thought I had a fairly developed idea, but I was thinking back to when it bid, and my idea was nowhere near what it actually ended up being. Actually, our original plan was to make something like what we were doing with a couple like 352 excavators without a stick on them, but the amount of weight and like sheer leverage that those things would have had, it would have not worked. But that was kind of the plan originally. But I think I probably had about 3 conference calls with Contech that were a little bit tough, because these guys are, as far as by these guys I mean Contech, every time they've installed them, it's been, an open cut. There's a crane over here, there's a crane over here, and you just put them in conventionally. And so everyone was very concerned because, these things are over $1 million in material.
And that's how it's typically done, is they're just
Correct.
putting in place. And
Yep.
then you move on.
The bridge wouldn't have been there. So you
Right.
could have ran 2 cranes on swap mats and put them together. So everyone was very concerned about, there's all this discussion and design, there's all this discussion and submittals and a lot of front end work just to make sure that it works and that it's successful, because, it's just as important that as me, the contractor, to get them installed, it is for Contech as the designer to get them installed. So we had a lot of meetings where it was like, no, that's not going to work, or, well, no, you can't have the crown bolt in, or no, you can't do this. And it was kind of frustrating at points, but I understand what everyone was trying to do is just to make sure that we didn't have a problem that was going to work. But, they kind of brought some stuff to the table. And by they, I mean Jake, and there was probably 3 or 4 different guys at Contech that were on these meetings. And then I had an individual doing some drawing, and he had some ideas there too. And, we had multiple different meetings and kind of started to go in the direction of, we need to have some sort of a deal where we can slide these things into place. And originally we were going to build the whole undercarriage just from the ground up, and we kind of drew it up. So originally there was like these little 8-inch wheels.
Like casters?
Yeah, like casters. And when we drew them up, how we had these 36-inch I-beams drawn in there that looked huge. And then we had these little 8-inch wheels drawn in there, and it just looked like a bad idea. So then I got to thinking, I was like, well, why don't we just get some rail cars? That's the whole bottom end. We'll just build off those. They're very heavy duty. They're very resilient. People use them for a lot of heavy weight and stuff, as far as like, running on the rail and stuff like that. So we kind of started to go that direction, and we kept all the false work above that the same with the hydraulics that we started to draw. We just put rail cars in there instead. And we got some conceptual things drawn up, and then it really took place a whole lot, I would say, when we started actually building it. So like we drew up a few things, we had a few meetings so that everyone kind of had an idea of what we were trying to do. And then we got the arches approved. We made a plan to get Weiser to build them. And, the big thing was get these first 2 built, get these first two Elkader. We're going to physically put them here, and we're going to take measurements with them mocked up, laying on the ground 90 degrees of the way they sit, so that we can make sure what we're building builds right into them and fits right into them, versus hauling all these, it's like 6 semi-loads of stuff that are, 90-foot long loads, and just really unconventional things to get down there, let alone getting them from the top of the hill to the bottom of the hill down into the creek. So we wanted to make sure we weren't making a ton of adjustments in the field. So we actually mocked up the whole thing in Elkader. So at CJ Moynihan and Sons is where they built all this.
But doing an arch on the ground would be different than doing an arch in the air with the weight of it bringing it down, right?
Yeah,
sure.
worried about that a little bit, that there's going to be some like deflection and stuff. And we did have to make some adjustments into the field. And I think we just had some measurements off. So once we actually got everything in the field, we put the 2 arches up, and we went to run the hydraulics up. We were like we basically hit, and then we were out of lift. So we couldn't get it up off the ground. So what we ended up doing is we put some big 12-inch by 12-inch beams in there, put our channels on top of those. And then we also made our channels adjustable, whereas they were just welded on there before, which we had to do because each arch fit just a little bit different in there. So we had to make some little adjustments every time we picked up to launch those arches in there. But I think it was really important setting all that up in Elkader and doing that. And, there's a lot of measuring and a lot of stuff to do there. But I mean, all the false work really didn't take off until we actually had these things. Cause like we've done stuff kind of like this, but not like this in scope and size and everything. And
Well,
it's hard to visualize how big everything is.
I don't think has anyone ever done an arch this size under an existing bridge with live traffic?
We've done close, but not the 2-piece. And again, I think what made this one extra challenging, and Travis hit the nail on the head when our engineers were talking to him and one of his mechanical guys who was helping him with drawings and sketches and everything, we almost didn't know what questions to ask. We didn't know what we didn't know. We just knew, first of all, this is a big arch. We got to make sure whatever we do somehow keeps it immobile and it's safe. You know, you got two really big slender pieces of concrete out there that if we don't figure out how to get it right away from the job site and we just go out there and not have a good plan put together, somebody could get hurt, or we're going to, you know, do future damage to the bridge or whatever. So the concept of being able to lift the whole thing into place also had to be able to lift it up into place over the footing, and then it also had to be able to lower it back down onto the shims, because the arches, in order to make sure we have equal loading on the bottom of the arches, we put it on a shim pack so they're not touching, because, you know, no contractor, no offense, Travis, is perfect when it comes to pouring concrete. So we use shims to give us a surface that once it's filled with grout and concrete in there, the leg is evenly supported the whole way. But that means you do need to lift the arch up all at one time, both leaves at the same time, and then set it back down. So the only way we really, Travis could kind of have the confidence to do this is we got to mock this up in Elkader. We sent out the arches early so he could get those finer points worked out. And I went down to Elkader and looked at it, and it was kind of funny. He was explaining it to me over the phone, and I have no idea what you're talking about. He's trying to send me some sketch and everything, and then I get out there and the light bulb goes on. Oh, this is what you mean now when you're putting these together. And it was one of those things you almost really need to get your hands on it and see it and feel it, how it worked and everything. Now, that's not to say we didn't have some bumps and bruises with the fine tuning and everything, but this was very big. Down in the job site, it doesn't look that big when you're in the parking lot in Elkader, you look at that, and I kept telling Travis, this looks like the Taj Mahal of steel I-beams. And then you're setting the Taj Mahal of steel I-beams right on top of the flatbed rail car. So it was a pretty genius idea, but it did need to be fine-tuned for sure. We might fast forward a little bit on the lessons learned. One of the things that I probably would have done differently is, and I'm sure Travis would have done this too, is we probably would have waited to design the MSE wall until he was out there looking at it. And we found this competent bedrock. You know what I mean? And maybe even a better way to approach that too would have had the exploration done ahead of time, and then we could have definitely had everything dialed in, and Schemmer wouldn't have had to redesign the elevations and the steps and the footings and everything, and we wouldn't have had to redesign the wall. It just probably would have made it a little cleaner and easier for all the parties involved. But again, we all got through it.
The math on, say, the 4 hydraulic cylinders, I mean, those things were all calculated. They were supposed to be able to pick up like 600,000 pounds. And obviously the I-beams, we had to make sure the cantilever that was hanging off, that there wouldn't be too much deflection there and stuff like that. So there was a lot of math and engineering that went into it. And for me, it was a big learning curve on figuring all that stuff out. So we weren't figuring out in the field that it didn't work and that we should have thought of it.
Travis, a quick point too, that is also a really big part of this, is it was more than just, you know, raising it and lowering up into point. You had to get the formwork back out of there to go get the next arches too. And that's why he had those doors in there, is you could go in there once you put the arch in, you got to be able to back out everything and repeat it and do it again. And that was part of what the brainchild had to be, was it had to have some extra features in it to be able to pull the Taj Mahal of green beams back out to be able to do it again.
Mm-hmm. Yeah, and we had these giant pieces of steel that had essentially like an angle iron on them, and then there was an angle iron on the structure, and that was what was all, like, from a shop drawing standpoint, where we put the holes where those would bolt in there. And we had multiple sets of those. I think we had enough to do 4 pieces at a time or 8 pieces at a time. So we'd put a whole bunch of those on there, and then, you know, they were all labeled for which side they went on, and we'd put them on there. And then when we dry fit those together and we had our false work below, we get them matched up like they're supposed to be when they're at the other end. And then we'd pick up our structure, we'd fine tune the angles, and then we'd pick up, just get it come off the ground just a pinch, we'd bolt everything down, and then we took chains and we pulled in, so we're pulling inward tension at all 4 points where our lift points were, and just to keep everything like sucked in like this. And then at that point, then we would pick it up and take it to the other end. And there was like a little learning curve of different things you had to do to get it set where it's set, because I'd always wanted to set with the top forward and the back, and there was a few things we had to do to make that work, and we didn't know until we brought to the other end to the next one, and we're like, I don't know,
Right,
why is it sitting like this? You know, and that I can talk forever on lessons and stuff with, you know, things we did in the field and stuff. There was just a lot of new and a lot of different stuff there. But I think the biggest thing that I could say is if, you know, that design could be more narrowed down. I understand things can change, but I think, you know, if we would have had some more exploration done pre-construction, you know, for the project to bid, that would have helped a lot. Because the biggest problem we had is by the time we got these things approved, you know, we're going to Weiser in like May, like, hey, we have these really complicated things that take up a lot of your yard that we need to get you in the schedule. Well, by then, you know, they got all these other things they're doing, and, you know, they don't know when they're going to start building arches. So it's not like they have just this window that's just there set aside for us forever. So they kind of need to make it work when it comes true, you know?
Yeah,
And that
so-
was the same thing for the MSC walls too.
Yeah, I think that's a great point. I believe what the intent was on the front end by probably the state, the initial design is probably the state thought, you know what? We've got this bedrock that we're not exactly sure where it's at. Instead of forcing it to a design to be a certain way, let's leave ourselves some flexibility so we can find out where it's at in the field. And I could see how that totally makes sense. I think when you get out there, though, you start thinking, wow, there's a lot that goes into the secret sauce to make the retaining wall. Everything from the strap distance, from the global stability overall. What do you do when you've got certain parts of the bedrock that aren't competent? You've got steps and all those different things. So I think probably Schemmer would agree too. And actually they came up in spades in being able to be flexible to jump on conference calls, redo the footing layout and everything. So that they stepped up and did a good job. And I think everybody did, but I think that was one thing that was maybe a problem that we could have avoided, as if we probably just did the exploration ahead of time and said, okay, let's get all the points we need, and then we can probably make this easier. So what was probably a good idea to say, hey, let's keep our field flexibility open, ended up being probably too difficult, because you got to understand too, Travis is also trying to manage water. So he doesn't want a massive hole that's left open every place to do explorations. He's trying to open it up as he goes to try to keep this site clean and not have a whole bunch of other issues and have extra pumps running. So I could definitely understand how it made sense on the front end. And I think when we got out to the job site and started looking how it played out, we thought, well, this might have been a lot easier on everybody to have that done up front.
Yeah, it's definitely a fun, different challenge. I've never solved so many giant problems in such a short period of time in my life.
Yeah, no, appreciate the opportunity to talk about it too, Derek. It's been a fun job. We knew it would be tough, but we're glad we got an opportunity to do it. It'll be a nice showcase when it's all said and done, and hopefully achieve the goals that the state was looking for at the start of the challenges with the detour and everything. I mean, it's easy to look at a job like this from the innocent bystander standpoint and say, why didn't they just do a detour through it? I'm sure if it were that easy, it would have been decided up front, right?
I mean, that's a pretty big deal to have a bridge of that span and that height replaced without shutting it down. I mean, I don't know if that's the seasons of work or seasons and a half to do something like that. I'm not a bridge guy, but to be able to keep a road open, I mean, yeah, it's pretty neat to be able to say. It's always really complicated to explain to someone what you're doing. They're like, so are you taking the bridge out then? It's like, no, we're not taking the bridge out. What do you mean? Never mind, I'll just show you some pictures. You know?
Oh, yeah.
I'm gonna say, I'm sure the motoring public, I don't know how many ADT that was, but I'm sure they appreciated the fact that they didn't have to go way around or whatever for a really, long amount of time.
Right.
This is one of it. I don't think this has been, I know as a company, we have not done a twin leaf under any bridge in the entire United States. So this will be a first of its kind. Obviously, we've done plenty of open cuts with two leaves, but never done underneath an existing bridge that stayed open the whole time.
Okay, so we're going to open it up now for questions. And Derek, Hugh Holick had a question in the chat. How was the stream diversion handled during construction?
I have Travis Augustine in here with me to help answer some of the questions. Travis, do you want to?
Yeah, so on the stream diversion, some of it was staging and then some of it was just putting in some temporary pipe. That time lapse video at the end, you can see the pipe. So when we did the north footing first, we kind of crowded all the water to the south, and it worked out nice because we were digging in limestone. So we would throw the dirt over, crowd the stream over, and then we could armor that stream with the limestone that we were excavating. There's probably anywhere from 4 to 6 foot of limestone, and we'd throw that right on the bank. So we just kind of crowded it over. And then when we got that footing done and then backfilled, we ended up putting in probably, I don't know, 300 feet of 60-inch concrete pipe along that footing. And then we pushed the water over to the north end into that pipe. And then we did all the excavation on the south side. And by the time this was going on the south side, we were getting into June, July, August, and 110-degree days and not a lot of rain. So we had a lucky season there last year. And the whole time we actually had to pull the pipe back out because it was in conflict with our false work. That's why in the time lapse you'd see that the pipe came back out because we couldn't get it by it. So we ended up just pumping it. We didn't really have that many pumps running during the low flow there. And you seen at the end of the video that it was flooded, but that was when we shut off the pumps. You know, at the end of the season, we had to call our quits around Christmas time. We came back in the spring and we had some challenges, I guess, with water getting it drawn back down. And we had, I think we had like a 3.5-inch rain a few weeks ago. So we had a 12-inch pump down there. We drew it down, but luckily we worked on the MSE wells trying to get them down to footing and then back up out of the stream area. And we had one we didn't quite get up. So surprisingly, we didn't have a whole lot of stream diversion issues for, I guess I would say, the amount of risk that's there, I guess. So.
That was the only question that was put in the chat. If anybody else has a question, you can certainly unmute your line and even turn on your camera if you want to ask questions of Derek and Travis.
Will the bridge eventually get tore out, or is that gonna just be filled up with mortar between the two and just left?
Yeah, the bridge never actually comes out. So right now the plans call for we go to within 12 foot of the bridge deck and kind of make a bathtub out of the embankment. That's as high as we can get the sand material in there, and then it'll get floatable backfill, you know, up to the bridge deck and around the beams and everything. And then we cut the barrier rails off the sides of the bridge. We core drill holes in the bridge deck to get the flowable in there. And then in that process or after that process, then there's an overlay that kind of ties everything back together and gets the holes and stuff covered back up there. So the bridge never actually comes out. And the biggest impact that the traffic has is for a short period of time, it'll be down to one lane with like stoplights. And we had to do that last fall a little bit just to handle some of the material deliveries. And we had the arches coming in. There was days we had, I think, 8 or 12 arches a day coming in. And then, you know, same thing with MSE wells. It's a tough site we couldn't really get them off the road.
Okay, does anybody else have any questions? All right, Derek, you did an awesome job explaining it. Apparently, nobody has any more questions. But if anybody does think of something later, you can always reach out to Derek, and he can get those answers for you from Jake or Matt or Travis. Thank you, everyone, for joining us. And I'm going to go ahead and sign us off. Thank you.